Hello, my name is Vitaly, and the topic of this video is how to design a flexible receive array of a parallel resonance high-impedance coaxial coils for imaging of carbon-13. MRI coils are typically operated either in an inductive or a self-resonant mode. The self-resonant coils can exploit a series or a parallel resonance and are often adopted as elements of flexible arrays. One example of a series resonant coil is air coils from GE. Parallel resonance coils can be realized using coupled conductors of a coaxial cable and have high input impedance at resonance. Therefore, they are sometimes referred to as high-impedance coils. The use of self-resonant coils at low frequency is challenging and requires longer cable length. To keep the desired loop diameter at 8 centimeters, we tune the coil to the resonance at 32 MHz using capacitor CT. Another useful feature of this coil is that the hydrogen decoupling can be integrated on the preamplifier printed circuit board instead of the loop wire. The active decoupling is achieved by shortening the terminals of the coil with a pin diode. The matching and decoupling network is based on a 3-element topology. This circuit matches the coil to the optimal noise impedance of the active device and at the same time provides minimum available impedance at the input terminals of the coil, realizing preamplifier decoupling. At the resonance frequency, the input impedance of the coil is approximately 1.8 kilo ohm when sample loaded. The design equations can be found in this paper. The effect of decoupling is visible when measuring with a double loop probe. This local minimum is the result of preamplifier decoupling. The coil is used as an element of an 8-channel array. On the right, you can see the measured noise correlation between all 8 elements when the flexible array is shaped for brain and neck imaging. And here you can see the photograph of the array with the cover removed. The preamp circuit size is a small fraction of the array, which supports the flexibility of the array. To minimize noise coupling between the channels, the coils are critically overlapped. The optimal overlapping is found empirically and corresponds to 25% of the loop diameter. Here you can see the results of the imaging experiments. In the brain position, the phantom could not be covered completely. This is the reason for slightly darker area on top where there is no actually active element. The ray imaging performance were also compared to the performance of the conventional wire loop coil. One can see that high impedance array has a slightly lower SNR in some places, which perhaps could be attributed to the accuracy of the positioning, while the noise correlation is a bit better. In conclusion, self-resonant high-impedance coaxial coils allow for convenient integration of the decoupling networks compatible with the flexible coil implementation. Hybrid co-integration of lumped and distributed components in self-resonant coils allows to tune the coaxial coil to virtually any frequency. This is particularly useful in low-frequency applications. The approach is used in the design of an array of parallel resonance coils operating at 32 MHz. The array is flexible, lightweight, and easy to handle due to flexibility of the implemented cable and compact preamplifier design. It is suitable for imaging various body parts and demonstrates low noise correlation. If you want to know more details, you are welcome to contact me by this email.